started. All right. Welcome, everybody. Welcome to the Brockhaus Institute for Materials Research seminar. And this is the focus sessions on microscopy. So my name is Nabil Basim. I'm a professor in the Department of Material Science and Engineering here at McMaster, and also the scientific director of the Canadian Center for Electron Microscopy. I haven't met all of you, but I know quite a few of you. See some familiar faces. So thank you, Alex and BIMR, for letting us spotlight this series of techniques. And we had Gianluigi Baton last week for the weather lecture. Today we have Jim Lebeau from MIT. Next week on Wednesday, it's a special time. I think it's the same room, but Wednesday at 1:30 we have Josh Caldwell from Vanderbilt University. And then the following Friday we have Lisa DeCecco, one of our alumni now at Waterloo, returning to give the BIMR lecture. So those are the 4 lectures related to electron microscopy, a little bit of optical microscopy as well. We'll let Josh come anyways. Yeah, so thank you for coming, and please come to the next talk and the next talk after that. And of course, keep coming to all the BIMR seminars. Okay, so our speaker today is Professor Jim Lebeau. He's in the Department of Material Science and Engineering at MIT. So I would say I can give a background that you can see it on the flyer. I'll just give a little bit of personal background. So Jim and I co-organized, or were co-organizers of the Microscopy and Microanalysis meeting in 2018 in Baltimore, which is like the biggest microscopy meeting, EM meeting in North America, probably the biggest in the world, maybe.
IMC might be the
IMC,
big one, yeah. I think.
And I had just moved from the States to Canada at the time, so Jim and I were working together, and he was a professor at North Carolina State University at the time, and he was like, what's it like up there? What's it like up there? And well, the CCM is great. It's a Shangri-La of microscopy. There's all this great stuff, all this great equipment. You can really do a lot. And so Jim was like, that sounds interesting. Maybe when I get my sabbatical at NC State, my first sabbatical, maybe I'll come up and spend some time with him. So a few years goes by. The microscopy gossip circles, all of a sudden there's a little buzz that goes out in microscopy. And everyone's like, oh, did you hear Jim had left? He went to MIT. So the next time I saw him at a meeting, I said, Jim, what the hell? You should have been coming up here for sabbatical instead you're going to MIT. And his response was, MIT is my sabbatical. So I'm not sure if that, you didn't get much time off, really, but I'm assuming you just hit the ground running there.
Yeah. Well, I had COVID hit immediately after I moved, so.
Well, that's also yeah. So finally, put in his time at MIT, finally he gets a chance to do a sabbatical. And so he's here, and he's been here since August, and he will be here through the end of the year, doing really interesting work, which you'll hear about very shortly, and bringing 4D STEM and Ptychography techniques to CCM, which is very fortuitous because this is one of the few areas we are quite weak in, so you're already helping us build up between the lucky confluence of Jim's sabbatical and bringing Alex Kapelski on board. We're really getting going with our Ptychography and 4D STEM, and you're going to see that this is some really awesome technique. You'll see it shortly, and then I want all of you in the audience, you can see how this technique could apply to your material system. Please talk to Alex and see if we can sort of duplicate this kind of great results, but for different material systems, not just you're going to present ferroelectrics, I assume.
Yeah, I think.
Not just ferroelectrics.
Yeah.
Okay, that's a very long introduction, but to say we're very happy that you're here, at least till the end of the year, and hopefully this is a kickoff for a lot of collaborations to come. So please, go ahead, Jim.
Yeah, thank you, Nabil. Thank you to McMaster for hosting me during this time. It's really great to be a part of the great facility and the characterization capabilities that are at McMaster. So what I'm going to talk to you about today is our work using in situ or operando electron microscopy to study devices, along with this newer technique called multislice electron ptychography that allows us to access information that was really unthinkable just 10 years ago, or even 5 years ago for that matter. This was really almost inconceivable that you could achieve this level of detail in our data sets. And so let's start back, just reminding everyone, in case there are those of you in the room that haven't familiarized yourself tremendously with scanning transmission electron microscopy. Let's start off with where the technique has come until basically 2020. And that is the technique of choice that we've had in my research is in scanning transmission electron microscopy, where we used to use an objective lens to scan a very finely focused probe on our sample, sub-angstrom size, and collect images on a point-by-point basis. So you built up the image in a serial manner, and you could do spectroscopy at the same time. The key thing about these techniques, though, is that you could build up a direct image of the structure, where in annular dark field imaging, for example, the brighter the atoms are in the image, the heavier they are. And the downside is you lost all ability to see light elements like oxygen, nitrogen, many of the key actors in ferroelectric and functional oxides that make that functionality possible. But about 10 years ago, a technique integrated differential phase contrast came on the scene in terms of what people were able to do routinely. And this allowed us to retrieve the information about oxygen and its position, even hydrogen in some cases, and build up these images. I'll show some downsides to this technique in a minute, but essentially aberrations of the microscope sample tilt make these this technique is extremely sensitive to those factors, and as a consequence, they don't tell you everything about the material and polarization specifically. It's not accurate. So that's just to give you a background of where we're of the general sort of area of STEM. But what I'm going to talk to you about today is using in situ operando techniques in STEM to measure and understand piezoelectric devices in the electron microscope, particularly based on antiferroelectrics. We'll then work into relaxer ferroelectrics, introduce the concept of ptychography in a bit more detail, and look at how we've applied this technique to study the strain and polarization states in this material with three-dimensional sensitivity. No longer are our electron microscopy data sets one-dimensional from one data set, I mean one image, one data set acquired, but we can get 3D information from that one collection of information. And then I'll finish up with our work on looking at chemical distribution in another antiferroelectric, but how we can use ptychography to explore also three-dimensional chemistry in a material and order disorder. Okay, so let's start off, just bring up everyone to the same page on ferroelectrics. So a conventional ferroelectric material, lead titanate, above room temperature is just cubic. I mean, no, not above room temperature. Above the Curie temperature is just cubic. And so it doesn't respond in the same way as a ferroelectric to an electric field. So with a ferroelectric, you have a built-in polarization, that is, where lead, oxygen, and titanium are offset relative to one another, building in a built-in dipole in the material. So that dipole can be switched with the application of an external field, and it allows you then through that application of that field to also change the unit cell parameters, and you get a piezoelectric response. That is, where you apply a field, you get a change in the unit cell dimension and a macro scale change in the size of that material. And these piezoelectrics are incredibly useful in actuators, transducer, energy harvesting, and storage, just as a couple examples there. But antiferroelectrics are quite a bit different than this. In an antiferroelectric material, you have a rather than a ferroelectric where all your dipole moments are aligned along the same direction, within the unit cell, the dipole moments cancel out. Half are pointing in one direction, the other half are pointing in the other. mean, you have net zero polarization. It has an inversion symmetry, center of inversion symmetry, and so that is not a ferroelectric, does not support a built-in polarization. But what happens when you apply an electric field to that sample? Well, you're going to have rotation of half of those, or really all of the polarization, to try and line up along the direction of the field. And as a consequence, you can change the unit cell itself, meaning you can go from an anti-ferroelectric, and if you apply a strong enough field, all those dipoles point in the same direction, it becomes a ferroelectric. And so if you look at a polarization versus electric field loop, what you'll find is that for these anti-ferroelectrics, you get a conversion from a linear dielectric, and as you apply higher and higher field, suddenly it changes. You have the net polarization, and behaves as a ferroelectric within each quadrant of that PE loop. What this gives rise to, as we'll see, are very large strains, and there are a lot of opportunities for engineering these materials through thin film engineering approaches, getting high ferroelastic strains, and can stabilize different phases through that strain. For example, AFE versus the paraelectric or ferroelectric. And so these have a lot of applications in capacitors, piezoelectric actuators, as I already mentioned. Now, coming back here for a moment, if we look at a ferroelectric like PTO, or a PZT, for example, your dipoles are going to rotate, right, with the field, and you get some strain out of that due to the piezoelectric response. Now, the problem is that if you grow the sample on a substrate, the substrate is going to want to clamp that unit cell and provide, basically lock in the structure so that polarization becomes less easy to rotate. And as a consequence, if you grow the bulk material, PZT, you can see it has a fairly large strain with relatively small electric field. But as soon as you grow a thin film now, you have to apply a much stronger electric field to get even a third of the bulk strain that you'd get out of the bulk material, right? That substrate is clamping it and preventing those distortions that would lead to a strong piezoelectric response. So to get a device means you have to go to a very thick film to get the response. If you go to an antiferroelectric, now you can, in PZO, get tremendously large strains, much higher than bulk PZT even, at reasonable values of the applied electric field. This is due to this transition between antiferroelectric to ferroelectric within that regime. But what's going on here ultimately is how does the PZO, the lead zirconate crystal structure, overcome that clamping and that antiferroelectric? And so what we ultimately need is information about what phases are present and the in-plane and out-of-plane strain as a function of bias. And these are very tricky experiments to do when they're growing on a substrate. You can go to a synchrotron to try and do this, but you need a synchrotron, and I don't have a synchrotron in my backyard. What I do have in my backyard is an electron microscope, and that electron microscope, paired with FIB, and with the latest advances in FIB, we're able to make these mini capacitor structures from those thin film capacitor structures grown on an actual device. So what we can do is FIB out and cut out that sample and build our little anti-ferroelectric capacitor. There is platinum on either side, so our substrate's conductive in this case. Our top electrode is also platinum, so it's conductive. We have a field basically being largely generated across the top and bottom electrodes, and the anti-ferroelectric is in between. And what you also see are these side cuts. Those side cuts disconnect the top electrode from this side and the bottom electrode from that side of the capacitor. So we have a nice out-of-plane field being applied, as we have shown in this diagram. Now we compare this with in situ microscopy, where we apply our bias, and also four-dimensional STEM, where we map the diffraction pattern at every point so we can measure things like the phase of the sample present, as well as the lattice constants to determine the local strain. And that, by looking at the diffraction patterns, we can immediately identify which ones are antiferroelectric by the presence of these satellite reflections over here that you don't see in a ferroelectric, where you have where those superlattice reflections disappear. All right. So the first up here is a thin film of PZO grown along the 240 direction on a substrate of strontium titanate. And we're going to collect our four-dimensional STEM. We're going to be able to measure then. This is really a two-dimensionally resolved data set, but I'm going to show you just the diffraction patterns to start, and then we'll see how this all changes on a point-by-point basis in structure in a moment. But what we can measure then from these diffraction patterns are the lattice constants, as well as the ferroelectric order, are the strength of those satellite reflections disappearing. So in other words, we become ferroelectric over here. You'll see these reflections disappear, and then they come back as we go towards 0 volts and back to -10. They disappear again. So you have strong ferroelectric order to either side. And we see some change in the lattice parameter. That strain, though, is very small. We're not getting a lot of response. But we can choose just one of those reflections in that diffraction pattern and map a two-dimensional distribution of the antiferroelectric phase. And that antiferroelectric is showing up as bright white here, with planar defects showing up. And as we apply voltage, you'll see that that largely disappears and comes back when we go to 0 volts, back at the middle. So we can watch these devices in action and understand the response back to their bulk properties. Now, if we grow that material on a different substrate that changes our growth orientation so that the 004 direction is out of plane, now what you end up with is a significantly different response. Instead, you see the ferroelectric order certainly increases dramatically as we go to high fields, but now the lattice constant and strain are tremendously enhanced. And it's through substrate clamping, in this case, that we actually force all of the strain to go out of plane from growing along this direction. And so this is basically a percent of strain that is in roughly the same comparison to what's measured macroscopically. And if you look at the diffraction pattern also from this case, you'll see that those satellite reflections completely disappear, and the other spots come in to indicate that antiferroelectric to ferroelectric order, and you can see how that's changing across the film. A couple of things to note is the whole film doesn't transform. Even at full bias, the film isn't fully transformed, and you also see that flickering. That's going to become important in a moment here. So all that I've shown you so far is what's going on macroscopically, relatively macroscopically, right? I mean, it's at the micron scale, but we don't see what's going on at the atomic scale in terms of what phases are present and where. But with modern in situ and operando type experiments in the electron microscope, we can actually apply a bias and watch the crystal structure respond at the atomic scale and create movies, essentially, of the atoms in action. And so here's an example from annular dark field STEM. Again, we're only seeing the cations here at 0 volts. As I start to apply a bias, you can see the shuffling of those atoms where it switches. That's the transition from an antiferroelectric to a ferroelectric at higher voltages. So again, just kind of showing here, as the switch is up to 8 volts, it becomes what looks like essentially cubic or tetragonal is what it's actually, it's tetragonal at 8 volts or ferroelectric. And so we can measure the polarization and find that we have this antipolar nature. Again, antiferroelectric polarization cancels out. At 8 volts, we get polarization alignment along the direction. Now, conventional DDPC or integrated differential phase contrast provides some information, but it's very difficult to really map out where all those atoms are at. But even here, we can start to see how the octahedral tilt changes from zero bias to this high bias, where you're seeing an octahedral oxygen, the octahedral cage rotating as a function of the applied bias that then you can map out. One of the things you notice here is this isn't perfectly uniform. You have inhomogeneity in that transition. And we can do this across the entire voltage range, mapping this out. You can see these defects pop into existence, these ordering, the stacking sequence ordering that then disappears into a ferroelectric rhombohedral phase that we can map out from that octahedral tilt. And this converts from rhombohedral into tetragonal at higher voltages and goes back to that antiferroelectric structure at 0 volts. And this is repeatable. So we're not just one measurement, but we can repeat the same experiment over and over and over in the microscope and get statistics on what's going on here. But one thing that we found, and one key thing at the atomic scale, is that you can map out some of these phase transitions. So what we'll find is that initially the sample starts out antiferroelectric. As we begin applying a field, the polarization begins to rotate such that you get this polar order that starts to pop in. It's ferroelectric but monoclinic. That monoclinic phase gives way to a rhombohedral phase as the polarization continues to rotate into the field direction. And then at full field and full transition, you go to the tetragonal phase. This was a new sort of phase along the path that's difficult to extract out from diffraction experiments alone, where you don't have the local scale information about what's going on and where. Partly it's because, again, this film doesn't fully transform. So you're always getting a mix of those phases within the sample. And a macroscopic paraelectric, a PE loop, goes through there, you get some shift going across the boundary. But one thing that we found is that the region near the interface, the reason it's dark here, is because it's not transforming at the bottom layers of the film. It's only the top half that's essentially transforming as a function of bias. And more importantly, we can track this as a function of field. And at a constant voltage of 6 volts, while we're imaging, we'll also notice these boundaries bounce around between the ferroelectric and antiferroelectric, meaning it's at a metastable condition, or it's being stabilized by that applied field. As the electron beam passes by, it applies an electric field that drags that boundary around. And so we can begin to probe sort of the energy stability of the different phases and the boundaries themselves with the electron beam as we're imaging at the applied voltage. This is not apply a voltage, then turn it off. This is with the bias constantly applied. And helps to understand some of the energy landscapes involved with transitioning from one phase to the next across these different frames and across the different polar order. Okay, so let me move on to the next exciting aspect, which is ptychography. And this is really, I think, within the next 5 years, people are going to be primarily doing electron ptychography in these types of electron microscopy experiments. As what you'll see here is really the power of this technique to provide insights into chemistry and the correlation with local structure. So let's talk about relaxer ferroelectrics. What we've talked about so far are conventional ferroelectrics and conventional antiferroelectrics, where essentially at a particular Curie temperature in a ferroelectric, you'll get a very sharp onset of a very sharp change in the dielectric function, in comparison to a relaxer, where this is a much more spread out transition in temperature, and as a result, you have basically, that behavior is spread out across a wider temperature range. And these relaxer study that we're going to look at today are PMN 30 PT. This is lead magnesium niobate lead titanate, a 30% lead titanate solid solution. It's a simple perovskite structure, lead on the A sublattice, magnesium, niobium, titanium on the B sublattice, and you get phase changes with increasing PT or temperature. And you also get a morphotropic phase boundary at 30%-ish PT. Now, in certain cases, particularly in PMN, pure PMN, this structure can order locally, where you have one sublattice of beta 1 here is niobium or magnesium rich, and beta is niobium rich, and it's not really fully ordered anywhere in the material, but you get this doubling of the unit cell as a consequence. And as a function of temperature and titanium content, you can change the properties of the material remarkably, where you get a dramatically enhanced electromechanical coupling enhancement at around 30% titanium or PT content in the material. You have a range of phases present from a rhombohedral monoclinic to tetragonal on the higher PT content side. But what this is allowed for is these to be used widely in a range of actuators, sensors, ultrasound imaging, for example. The other thing to note is the PE loops are very narrow, so they don't have a lot of hysteresis in comparison to a more conventional, strongly ferroelectric material. So what we have in understanding the origins of this diffuse nature of the dielectric properties, for example, is that it's been postulated there were these polar nanoregions in the material. Those polar nanoregions would be regions where you have net polar dipoles that are aligned randomly relative to one another, but that interact and coexist with the normal ferroelectric domains that surround them. And they can be due to a whole range of inhomogeneities of the system, a mix of chemical and structural disorder, even subtle picometer scale displacements that is evident from diffuse scattering. So rather than nice sharp diffraction spots, you always end up with these, they look a bit more like butterflies in neutron and X-ray diffraction, hence why they're called butterfly diffuse scattering. But here, this sort of streaking is due to that local, those local effects. And it's largely inferred from diffraction studies. Directly identifying what's changing and where is much more challenging from X-ray than looking at it directly in the electron microscope. But this is why, for many years, this has been referred to as a very frustrating material system, because it's basically reminiscent of this old parable, I suppose, where you basically have viewing these materials with different techniques give you different answers. And that's not the case, or that's, it's led to a very confusing material system as a consequence. And it was normally thought that they were kind of a hopeless mess to really understand what the origins of this relaxer ferroelectric properties were. So in conventional STEM analysis, we can try and apply this to these materials, and that's what we had done previously. And what we can do is use this to identify where our magnesium, niobium, and titanium columns are, and map out their displacements relative to lead. These would be what were often used as a proxy for understanding polarization in the microscopy community, but it didn't include oxygen. So you got displacements of your cations, but if you only have cations, a dipole that does not make, right? You have to have oxygen. And so going on to other techniques like combining that with integrated differential phase contrast, you could measure out where your oxygen positions were, but then if you compared, first off, with polar maps from composition, what were considered polar maps from composition, or from the cations versus cations and anions, you get very different results. And the other thing to remember about STEM imaging is that when you capture an image, you're primarily capturing the surface information. If you acquire one image in focus, you're capturing a very narrow portion of that sample. It's not the full depth information. Everything gets otherwise squashed down into into a 1D plane, primarily from the surface of the sample. And so, even so, those techniques had provided a lot of insights into relaxers, but they weren't the complete story that could be directly compared with techniques like molecular dynamics or density functional theory to validate both the technique itself, but also to validate models that have been created of relaxer ferroelectrics. And that's where electron ptychography comes into play. Previously, again, we were losing a lot of information because all that we could acquire was from diffraction and imaging was intensity. Anytime you make electron microscopy is fundamentally quantum mechanics. And as soon as you measure something, it's the intensity. You've lost all phase information about the electron when it reaches the detector. So in addition to that, electrons are pesky in that they scatter dynamically within the sample. They really like to scatter strongly off the nuclear cores of the material, and as a result, this makes interpretation very difficult. You cannot use kinematical approximations in these materials like you can with X-rays. So to overcome this issue, we use a defocused electron probe, and this is what ptychography is. We use a defocused electron probe. We scan that across our sample. We collect this with a high dynamic range detector, in our case an MPAD, electron microscopy pixel array detector that was developed at Cornell. And by mapping that across, what you're seeing here is phase contrast information from the lattice being projected into that detector. I'm moving my probe across the sample and it's illuminating different regions. As that probe is scanned, it is tracking the same region. So that is the same atom, meaning that there's overlap between those probe positions as I'm scanning, right? So I know that those probe positions are connected by some phase ramp applied to my probe that is being scanned across the sample. And essentially, that's all the information I actually need to recover what that object was and the incident electron probe. This is a very highly redundant data set with a lot of overlap. So I have there are a lot of variables in this, but I also have a lot of data to solve for all of those variables as a consequence. And so from that overlap information and from iterative reconstruction methods, we can recover the object amplitude, the object phase, and recover the probe phase as well. So from that one data set, as was shown in the Muller group in this science paper in 2021, for example, resolution gets down to, of this technique, you're essentially deconvolving dynamical scattering and deconvolving the electron probe. You can go down to 20 picometer-ish resolution of your object. And because it's dynamical scattering, this encodes three-dimensional information within that data set, and you can recover that 3D information as well by resolving this onto a series of slices. So it's not just one it's not just one image, but one data set can give you 20 images, 30 images from the same object, all with different information. And so we spent some time really working out what are the optimum parameters for what we were trying to do, and we developed a couple of parameters that we could use to map out basically the experimental parameters and wrap them up into these area oversampling, which is basically how much each probe position visits each point on the sample, and the Rankine magnification is how much information is magnified within that disk that we had illuminated over our sample. And by plotting these out, we essentially have a region here, roughly a line there, that will give us essentially reconstructions essentially every time. The red dots that sort of bleed over here, these are just small convergence angles that make convergence more difficult. But we really have sort of a line essentially of go, no go of whether or not your data is going to reconstruct based on the convergence angle, how finely you've sampled stuff in reciprocal space, that's this theta, and then how big your probe was in real space. From these three variables alone that build into these parameters, it really does have a very good prediction capability. And we've done this by looking at a whole bunch of data sets that were acquired from the same sample, all with different conditions. And if we acquired those data sets that passed the criterion that I just sort of laid out and the parameters that I just laid out, we would get nice reconstructions. If they didn't pass, they wouldn't converge, basically. But none of them passed but didn't converge. So you essentially get to 100% yield, and that includes samples, hafnia, silicon carbide. It's not just one type of material. And more importantly, if you need a large field of view, you can change the way you acquire your data so that you can get 1.4 angstrom spacing between the positions in real space to give you resolution that's still on the order of about 20 to 30 picometers from 1.4 angstrom probes. So what this means is you can use a fairly small number of pixels in real space and get a much more finely sampled and much higher resolution than you would conventionally. So much lower dose on the material, etc. And this gives a 30 by 30 nanometer field of view is readily possible. Now, as I said, we can readily apply this to a broad range of samples: aluminum nitride, silicon carbide, lead, magnesium, tungstate. Atomic number doesn't matter. Thickness of the sample limits out at about 40 nanometers, 40 to 50 nanometers or so, depending on the atoms present. But the technique works, it's reproducible, and we've gotten fairly routine acquisitions at this point. And just to compare here of coming back to this lead, magnesium, niobate, lead titanate sample, IDPC imaging, you can see oxygen. But when you go to, when you go to ptychography, I think I just muted the thing. Yeah. When you go to ptychography, that's the result. Now you can really see where oxygen is at. You can see where the cations are at. Now you can really measure polarization. And not just polarization in two dimensions, but polarization in 3 dimensions, as I'll show. So now looking at that, looking at a small section of a data set from experiment, this is just one region. This is a sum of all the slices that we get out of the sample. So this is a 3-dimensional object that's been squished down to just 2 dimensions. And what you'll notice here is that some of the lead columns look a little bit more smeared out than others. This one seems really sharp versus these down here that look really smeared out. What's going on? Well, we can uncover what's going on by taking line profiles along this direction here. But what I'm mapping out is the intensity as a function of depth. And what I'll see here is that as I go down that lead-oxygen column, at a certain point, the lead-oxygen column actually flips at 2 different positions, right? And oxygen staying the same position, the B sublattice, that is magnesium, niobium, or titanium, all stay locked to the same position. It's the lead that's responding to the local chemistry, and we're essentially seeing a 180-degree domain rotation of the polarization through the depth of the sample. This is sort of was unthinkable in terms of what you could do from one single data set acquisition on the microscope previously. And so these types of information is really the 3-dimensional displacements being able to be extracted through the depth. Now, how well does this actually line up with, or from theory, what would we expect to be the case? And for ptychography, we can simulate a structure using molecular dynamics to get the polar displacements as a function of position, and then simulate a 4D STEM data set, and then reconstruct it. And so that's exactly what we've done here. This is the directly calculated projected potential on different slices from molecular dynamics. You can see those displacements, basically the local polarization changing across. Those are the reconstructed slices from that same position and the measured polarization. Basically, you get a one-to-one correspondence. And it's not even just visual correspondence, but quantitative correspondence. So those measured projected displacements from the projected potential and the measured from the reconstructed. These are extremely close to one another. We're really measuring where those atoms are displacing with three-dimensional sensitivity. And more importantly, are we seeing something that's stable from one data set to the next? So we can go ahead and repeat the same measurement, the same 40-stem data set acquisition over the same area, reconstruct it. These are just different timestamps. These data sets were acquired and reconstructed. You get extremely good agreement through the entire stack. The same thing with ones that are acquired over a much longer period, from an hour to a few minutes. We get essentially the same structural reconstruction from the same region. The polarization is really what the sample is doing. It's not something that comes out of the mathematics. And it's even consistent between adjacent regions, so I can march across my sample and reconstruct those regions that are right next to each other and then stitch them together and build up large-scale, longer-range, mesoscale sort of information for comparison with theory. So it's not just, a 1 nanometer by 1 nanometer by, X nanometer thick. This is tens, if not hundreds of nanometers by hundreds of nanometers that we can acquire data from and extract out information about polarization, dopants, interstitials, defects. Single defects in a material are extractable through this technique. All right, but let's zoom in here for a moment and look at just one of the data sets. In 3D. What you're seeing here is a map of different polar nanodomains and how they relate to each other in 3D. We can map out from that volume essentially the polar domains. That's the different color, would be the self-similar domains. And then we also have polar domain walls. These would be low-angle domain walls between different ferroelectric domains. We also find as we go up in higher strain, higher angle domain walls start to form. Here, even a head-to-head polar domain wall. What was interesting about this is that that's a high-energy domain wall. If you look at the theory calculations, that was unexpected. You would not expect to actually find that, and I'll show you why in just a second. But again, you start to pull out all this information. You can interrogate how much what the potential is basically at every point in your image. This would be a template average over a large area. But what this allows us to do is look at how, if it's more niobium rich, that would be more red basically, you get displacements of lead being pushed out and oxygen being pulled towards that middle lead, or the middle B sub, this cation. As it's more positive, it wants to drag in the negatively charged oxygen. The positively charged lead wants to go away. And so you can get this chemical information directly from these maps on a very local basis. These are unit cell level displacements. And doing polar principal component analysis, for example, allows us to, on a statistical way, look at how these polar motifs, if you will, change across a sample. And as you increase in strain, you become more polar along a single direction, whereas the 0.5% strain, lower strain states, still preserve more of the sort of sources of polarization that you can find locally around niobium and magnesium. Okay, so taking this a step further, we can do a lot of statistics over all these data sets that we have by looking at what's our correlation, basically an correlation of angle map here. And what we're doing is essentially look at the neighbors in the neighborhood of a certain atom and looking at the correlation. And so for different angles, if I am off at this 0.5%, what you would notice here is that there's a lot of polar disorder. As we go up in higher strain, more of the lattice is pointing in the same direction, right? You can see that visually, but now we can map that out statistically to understand and compare with theory. So these are our experimental results. you have largely correlation at a very local range. As I go further and further out, that correlation falls off to sort of a constant level, meaning as I go down here, I can get any polar direction. That's why that's purple. As I go towards higher and higher strain, I only get two configurations, basically, that we have 180-degree rotation between two domains. That's what we're seeing in these maps, and we can basically measure correlation length. Now, that's important because we can do the same thing from MEP, ptychography, as we can do from molecular dynamics calculations. And if we try and compare these molecular dynamics calculations using, this is a little bit coming down to but this is a local, it's a random site occupation of an ordered lattice, essentially, of the magnesium, niobium, and titanium. But important thing is there's chemical order in this case. And what you see is something very different from what we see experimentally. So these would say theory isn't right. But that's because the theory was simply taking into account chemical order, even though this is at 30 pt. At 30 pt, you get a breakdown of chemical order in this material, and those, this occupancy of magnesium, this double perovskite just becomes completely disordered, essentially, almost. But when you do that, fully disordered, now you get much better agreement between the experiment and the calculation. Reality is somewhere in between because, in fact, in our experimental data, we still find chemically ordered regions. This is found by using basically the phase on the magnesium, niobium, and titanium columns. And you can see local regions of order where you have bright a red, blue, red, blue, red, blue over here. This corresponds to a local chemical ordering of magnesium-rich, niobium-rich. The weaker the phase, the more niobium, or the more magnesium. The stronger the phase, the more niobium at that position. And so we can map this out and actually find that this agrees very well with what we'd expect from the calculations. So in many ways, the experiments validated a theory, but the theory also was validated by the experiments, that we can really find these sorts of distributions in both. Oh, and the other thing, as I mentioned, these cases have these head-to-head domain walls. This never occurred in the random site model, but when we added chemical disorder, to that, there you start to end up with these head-to-head domain boundaries again. This would have really been, it did not occur otherwise in the models without including that composition. All right, so the last few minutes here, just wanted to talk about our work on this other antiferroelectric, lead-magnesium tungstate. I won't go through the details here other than to say, because it's what we really talked about before, but in this case, it's strongly ordered. Magnesium and tungsten have charge states of 2+ and 6+. They want to get as far away from themselves as they can. So they form this ordered lattice on the B sublattice of magnesium, tungsten, magnesium, tungsten, magnesium, tungsten in a very ordered configuration. It's difficult to grow, and it does have some interesting properties, particularly for electrocaloric effects and transitions. When we looked at the films grown on an STO substrate, what we found are these vertical domain boundaries sitting in the films with a sort of, what do you want to call that, a little, a slow rise, kind of a mountain with a very high peak, I suppose. If we look closely at those, we would always find a boundary here that looks chemically disordered. And what you find if you go march across the B sublattice is that this is an anti-phase boundary, meaning the unit cell is offset by half a unit cell going along the vertical direction. They're offset. So when I bring these two offset parts of the crystal together, I would try and align tungsten and tungsten, right, from the octahedron. They'd be right next to each other. As a consequence of that, they're going to be very high charge state. And so you might think it's going to chemically disorder to try and decrease that charge. But the important thing to know, they appear chemically disordered, but are they? The problem with using high angle annular dark field STEM is that you can get many results that are ambiguous and that are not easily distinguished with using one image alone, or even defocal series can be very ambiguous as well. But there are alternative explanations for that same contrast. One is that it's just random, so this would be through the thickness of the sample, this direction from top to bottom. The electron beam is along that direction from top to bottom. In this case, a random alloy gives me that middle contrast. An inclined boundary would also give me the same sort of contrast, and a step boundary would also give me that exact same contrast. So which is it? From, again, STEM, you'd have to do a lot of work to try and resolve that question. With ptychography, we can acquire one data set and get the answer. So again, here's our HADF image. Here's ptychography. Now, rather than just the heavy atoms, you also get oxygen for free, and you can get chemical sensitivity out of this with three-dimensional information. So what I'm going to show here is a little video of our multi-slice reconstruction, and each frame of the video is a different slice along the thickness, right? And what I'd like you to note is that as I play that video, you probably can't see anything, right? It's very difficult. That's because the contrast of ptychography is so high in comparison to what you're normally looking at in one of these HADF images that it gets hidden. But what we can do instead is to map out, it should have been overlapped on that, but what you can see is there's this boundary here. The chemical order of the magnesium and tungsten are the blue magnesium and red tungsten sites, but at the boundary you get this white contrast moving across that image. That is, why is it moving across the image? Because the boundary is inclined relative to the electron beam. And we can also see this chemical intermixing. So let's just look at the simulations, compare them to our experiment. If we had a sharp inclined boundary, this is what we would see. Very sharp all the way through. Overlay step boundary, and a random site model would just be blurred in the middle basically throughout the entire stack. In our experiment, again, moves from left to right, meaning it's inclined, and there's some diffuse scattering or some diffuse nature of those components at the boundary, indicating that there's disorder and an inclined boundary that we're seeing. The boundary is much narrower than that blurring or that image intensity would suggest. This is driven by, again, that unstable alignment of tungsten next to each other. We can also measure antiferroelectric distortions across here. If we measure the lead-lead distances across here, you see this ordering of red, blue, red, blue, red, blue across here. This is due to the antiferroelectric structure of lead, magnesium, tungstate compared to the paraelectric where they're just equal. And again, it marches from left to right. We can reconstruct the thing in 3 dimensions to find that what we're really seeing across that aligned, occurring at the inclined boundary is not just chemical change, but also property change, meaning we have a dipole alignment of that antiferroelectric structure on that plane as well. So we seem to have local chemistry that is stabilizing that antiferroelectric distortion. It's shown in a little bit better, clearer detail of the 3D volumes overlapping between the antiphase boundary and that chemical disorder. And finally, we can map out those two and do some statistics of where our polar order is and where that boundary is, and the chemical or the antiferroelectric aligns right at that position. Right. Okay, so to very quickly summarize, we can do Operando STEM using, applying an electric field in the microscope allows us to really study the structural responses, the phases present, and ultimately, at the atomic scale, what gives rise to property changes. With ptychography, with multislice electron ptychography, we can reconstruct the functional properties of materials that have really been out of reach previously. These very complex materials with a lot of chemical polar changes, chemistry and polar changes, and phase changes through the depth of the sample can now be extracted. And as well, we can even look at chemical disorder locally on different types of, or in this case, an anti-phase boundary to understand its influence on local structural distortions that can, again, modify the properties. So with that, I'd like to thank all the collaborators on these projects, working with Lane Martin's group, particularly John Spanier's and Andrew Rapp's group, and the student, or was student at the time, Michael, now postdoc in the group, and Munglan and Colin. And most importantly, thank all of you, and leave you with a little bit of atomic res art. This is a multi-slice electron ptychography data set of silicon carbide. That wiggling that you see there is the result of ion implantation. That is the damage of the lattice due to implantation of atoms that then can be extracted with ptychography. So with that, thank you all for your attention, and happy to take a few questions.
Questions for Jim?
Very interesting, thank you very much. Regarding to this discrepancy between the theory and your observation,
Yep.
you are using essentially molecular dynamics, which is dependent, strongly dependent on the type of the potential.
Right.
What would happen if you would use a DFT, for example?
So those were trained off of DFT. So those are DFT trained potentials. Those are not, yeah. Those are calculated potentials. Yeah. Fundamentally, it comes down to what the assumption about the B sublattice cations that are put into the molecular dynamics that then gives rise to, basically, if it doesn't match the experiment, it's not going to match the yep.
Okay, I got more questions?
Well, if you like it,
Keep going. Yeah.
So you know, this you were showing essentially antiphase boundary and how it is inclined in the point. It's not a large angle grain boundary.
Right.
It's antiphase boundary where you have a different dipole moments in two areas, and that's why you've got essentially within the single crystal, you've got this antiphase boundary that is inclined.
Right, and I mean, ultimately, when it starts off growth, if it starts off on the half plane or the, one of the, like the 001 or the 002, it's going to end up forming an antiphase boundary automatically. So it's sort of just where it nucleates on the substrate is going to dictate that there has to be any phase boundary.
It's still very amazing because you've got really a perfect single crystal.
Yep.
Diffraction and whether diffraction or the direct image.
Yeah.
Yes, that's very interesting. Thanks.
Oh.
Yeah.
Yeah, so you mentioned that 40 nanometers is kind of the limit for this. What's the reason?
Yeah, so you can think about it this way. The way that these reconstructions currently work and the ones that we're using, they essentially have, it uses one object. What that means is that the potential is essentially blurring out to accommodate the fact that you have thermal motion, for example. But that would be equivalent to an absorptive potential in conventional calculations, like if you've done or know of like block wave calculations. That is how they would be done, with an absorptive potential. Now, there's also what's known as frozen phonon calculations, where you have sharp potentials but displace them randomly and then average together the results incoherently. What that can actually reproduce is quantitatively to a much thicker sample. It's just much more computationally expensive. So using absorptive potentials is cheaper and easier and much easier to implement, but it does hit that limit at about 40 nanometers thick, 30. It depends on the sample, but the atoms present in density, yep.
So aberrations will not interfere.
To an extent. The way that aberrations can mess you up is that if your aberration function is varying very quickly, then the coherence effects in the detector are changing within 1 pixel. Any time the phase changes within 1 pixel, it cannot be captured by the detector at that point, and so it gets washed out. So as long as your probe is relatively, the phase change is relatively flat, not doing this, you'll be fine. But that's the limit there.
What if I have a textured metal film?
Textured metal film, yep.
Textured metal film with a dominant texture axis, but I can't get the whole zone axis in each sub-columnar grain.
Yep.
How far can I get with ptychography?
So it depends on the size of the grains and what you're trying to accomplish, but you can correct for tilt with ptychography. So if there's a little bit of mistilt of, say, less than a degree, but like 10, 15 milliradian, it's about a degree, but you can incorporate that into the scattering model, and for the different regions, basically put the propagation, or account for that propagation difference between the two and undo that tilt and recover the resolution that I've showed. But beyond that, you have to start to think about taking multiple data sets, multiple ptychography data sets at different tilts, and then reconstructing through a combined model, basically, that includes all that data. But that's also possible. It all depends on how long you want to wait.
Yeah, no, so I was just thinking, so you essentially are doing either over-focus or under-focus as you scan the section.
Now, to say, one thing I will say is you can do in-focus ptychography, but I think there's a lot of benefit to doing out of focus for various reasons.
That was my question. So
Yeah.
if you would add the through focus series, wouldn't you get some extra dimension to the data and extra information?
Yeah, I think you're better off tilting to get more, because it's sort of, it's the difference between kind of just getting closer to an object or further away from versus looking at it from different angles. Yeah. Yep.
All right, let's thank our speaker. And